Hi everyone, this is Naoto Saki. In this webinar, I like to discuss my recent results, which are hopefully related to quantum chaos in quantum spin systems. In particular, I discuss imaginary time evolution of operators and something called operator growth. The paper is still in preparation, but the appendix of the paper that I wrote with Naoto Shiraishi contains some results that I present in this webinar. Okay. And I believe some of you are very much familiar with this famous short story from Jiangsu, and probably some of you can read this. But anyway, I will come back to this later with an English translation. Okay, so let me start with my motivation. Very roughly speaking, there are two distinct approaches in mathematical studies of quantum many-body systems. In one approach, you try to solve models exactly by using some clever method. Okay, this is nice, but of course, by definition, this kind of approach applies only to integrable models. In the other approach, you try to prove rigorous theorems for some general class of models. Okay, usually this kind of approach applies both to integrable models and non-integrable models. But in reality, there are properties or phenomena like quantum chaos, thermalization, energy eigenstate thermalization hypothesis that are expected to take place only in non-integrable systems. Okay, so then a natural question is, are there mathematical rigorous results that exclusively apply to non-integrable systems? For quite a long time, I thought the answer was no, and I think I was right. That's why I was so surprised and excited when my young friend Naoto Shiraishi came up with a beautiful proof of the absence of non-trivial local conserved quantities in the spin 1/2 XYZ chain. As you know, if an unintegrable system usually have a bunch of conserved quantities. So this shows that it's very different from integrable systems. So in this case, this proves that a concrete quantum model exhibits a behavior that is never observed in integrable models. Okay, and for some time I believed that this Naoto's result was the first of this kind, but then I learned that back in 2015, Gabriel Bauch proved very interesting result for this particular two-dimensional spin system. And it's about the imaginary time evolution. I will talk. Actually, this is one of the main topic in this this webinar. And also in 2021, Chanyu Cao proved very interesting result about operator growth. So I'm not going to discuss Cao's result here, but our topic is closely related to this one. Okay, so let me go on. So let me start by definitions and main results. Okay, so I consider a spin 1/2 system on the d-dimensional hypercubic lattice ZD. So it's infinitely large, and U denotes a lattice site, and then X, U, Y, U, Z, U denote copies of Pauli operators on at site U. Okay, and then this is a standard object called the algebra of local operators. It's simply the set of all polynomials made of X, Y, Z. Okay, so it contains any operator that acts on a finite region. Okay, this region can be huge, but it must be finite. Okay, so that consists this local operators. Okay, and here is our Hamiltonian, which is rather formal. So anyway, this is a very standard Hamiltonian with XX, nearest neighbor XX interaction, YY interaction, and ZZ interaction. And here's another standard magnetic field term. Okay, these are just coupling constant and magnetic fields. Okay, but I say this is formal because I sum over all infinite lattice. Okay, and this, of course, does not belong to log or any operator algebra. So more well-defined object is H lambda, where lambda is a finite subset of ZD. And then this H lambda is defined by restricting UV in this sum or U in this sum to those belong to those which is those in this finite region lambda. Okay, then this is an element of this is just a local operator, and it's just a finite dimensional matrix. Okay, Right, so this is something related to Naoto's work, and this is a side remark about the absence of non-trivial local conserved quantities. So we consider this standard Hamiltonian with spin 1/2. Then we prove that in all models in dimension 2 or higher, except for the classical Ising model. By classical Ising model, I mean something like this. So if you don't have this, and if you don't have this, and then you have standard classical Ising model, or the same thing for this and this. Okay, so except for the classical Ising model, we can prove that there exists no non-trivial local conserved quantities. Okay, the result for quantum Ising model was proved by Yuya Chiba, and we proved the case for xy and xyz. And as I said before, usually integrable system have a bunch of conserved quantities. So this gives us a strong indication that all these models are non-integrable. And as I said, this is a straightforward extension of Naoto Shiraishi's groundbreaking work in 2019. And if you are interested in this, actually, there is my online graduate level course called Advanced Topics in Statistical Physics. And one of the mini courses is called Integrable and Non-Integrable Quantum Spin Chains. Here I discuss how to solve XY. This is Elliott leaf. And how to solve XY chain and how to prove that some version does not have local conserved quantities. Okay, so if you're interested, please take a look at this online lecture. And I also like to remark that now there is extremely rapid and essential progress in this direction. So there are many new general interesting results have been proved. So please check arXiv about the recent progress. Okay, so this was just a side remark, and this is not the main topic of this webinar. Now let me go into the main topic, and I consider time evolution. Okay, so I take any local operator. It's local, just a finite dimensional matrix. And this is the time evolution in a finite system. Okay, so again, H lambda is just a finite dimensional matrix. So by only using linear algebra, you know that this time evolved operator exists. That's okay. But we are interested in this infinite volume limit. Okay, so H depends on lambda, and we want to make this lambda subset infinitely large. Does the limit exist? Actually, it is known, this is a textbook theorem, it is well known that if t is real, and usually t is real, this infinite volume limit exists for any initial thing and any real t. Very nice. And actually, the limit is not in this lock. You have to slightly extend the space by taking the completion with respect to the operator norm. But if you don't care about such thing, you don't have to care. So anyway, the limit exists. And actually, this is proved by using the Lieb-Robinson bound. The Lieb-Robinson bound is recently used to prove many fashionable things. But it was originally developed to prove this textbook theorem. Okay, so this is for real t, and that's natural. But back in 1969, Araki, of course, this is famous Professor Fujihiro Araki, proved that if you're in one dimension, then this same limit exists for any, of course, initial operator and any t which can be complex. Okay, so this is a very interesting theorem, and also it was useful. It was used by Yoshiko Ogata to prove her beautiful large deviation theorem and so on. But this is for one dimension. What about two dimension or higher? It remained open for quite a long time. But first of all, I want to remark that if the absolute value of t is bounded by some constant, then this limit exists for some trivial reason. So that's easy. But what happens if the absolute value is large? Then in 2015, Bauch proved this very important theorem. There exists a model in two dimensions, and this is the model Hamiltonian. It's a bit artificial, but anyway, this is a concrete, simple model. And he proved that here the limit is this. This limit does not converge for real beta with sufficiently large absolute value. Okay, so here is one remark. Some of you might think that you are familiar with this imaginary time operator, but usually this kind of operator appears inside the thermal expectation. Okay, then it's related to the KMS condition and it's something natural. But I want to say that this is a rather exotic object. Okay, we are considering the operator itself, time-evolved operator itself, when time is pure imaginary. So that is the object. And in 2020, Avdoshkin and Demarsky made a very interesting conjecture about the relation between this imaginary time evolution and quantum chaos. Okay, so here is this operator, which is pure imaginary time evolution. And then they argued, they said that in an integrable system, this operator with real beta grows in space at most polynomially in the absolute value of beta. Okay, but they say that in a chaotic system, this operator grows with real beta in the fastest possible manner. And in this fastest possible manner, in one dimension, is double exponential in beta. Okay, so this is still consistent with Araki's theorem about the existence of infinite volume limit. But they argue that, well, this is consistent with what Bauchi said. In dimension 2 or higher in a chaotic system, this operator reaches infinity at a finite beta. Okay, so there's no leap, no leap Robinson, no leap, no Robinson, no nothing. And this is related in an essential manner to the universal operator growth hypothesis that I will discuss very soon. Okay, so what is our contribution? Well, so we took this standard spin 1/2 model in dimension 2 or higher, and then except for the classical Ising model, we proved that this operator for some initial operator does not converge for beta, real beta, with sufficiently large absolute value. Okay, this is partially proved in our paper and also will be proved in the paper in preparation. So this extends Bauchi's theorem to standard spin models, okay, described here. Okay, but anyway, this was a case in which we believe that the model is non-integrable. What about integrable models? Well, there are not so many integrable models in 2 dimensions, but this is a famous Kitaev honeycomb model. If you don't know about this, well, it's an interesting model. And anyway, this is not a difficult theorem, but in this case, I can prove something similar to Araki's theorem. So in the Kitaev honeycomb model, the limit, the infinite volume limit HE exists for any initial operator and any complex T. Okay, so this result for the non-existence of the limit and the existence of limits are perfectly consistent with the conjecture by Avdoshkin and Demarsky. Okay, so that's one main result. Okay, so let's change the topic. And now I'm going to discuss something called operator growth. So this slide is a bit complicated, I'm sorry, but okay, let me explain. So first of all, I will define something called normalized Hilbert-Schmidt inner product. Okay, so let A and B be local operators. And then I define this inner product this way. Well, this is basically Hilbert-Schmidt norm. So inner product. So I take A dagger B and you trace. And this H lambda is a Hilbert space, finite dimensional Hilbert space corresponding to this finite subset lambda of CD. Okay, and and this is of course well defined, and since everything is finite dimensional, and if lambda is large enough, to contain the supports of A and B, and then this no longer depends on lambda. Okay, so this gives the definition of this inner product. I also define the Lindbladian, or if you're a mathematician, you want to call it generator of time evolution, called delta of A, and this is basically the commutator with Hamiltonian. Okay, and sometimes you don't put I here, but I want to put I here because if A is self-adjoint, then this also becomes self-adjoint in this case. But anyway, again, this is a commutator with Hamiltonian in a finite volume. And again, if this lambda is sufficiently large to contain the support of A, then this commutator does not depend on lambda. So we have this well-defined object. Okay, all right. Now I take a arbitrary initial, some your favorite initial operator A. For technical reason, I want to assume it's self-adjoint and it's normalized with respect to this Hilbert-Schmidt inner product. Okay. Then consider this series, A delta squared. So this means that you start from A and take commutator with Hamiltonian and double commutator and another commutator. You take many commutators with Hamiltonian. And I think everybody will agree that this series contains some very important information about the time evolution of the system. Okay. But it is known that in order to characterize the system, it is better to look at the Gram-Schmidt orthogonalized version of this series. Okay, by Gram-Schmidt orthogonalization, I mean that first of all you take O0 to be A itself, and then On consists of first of all this thing, and I don't put any normalization condition here. This thing, the nth recursion, and a linear combination of all these recursions for j from 0 to n minus 1. And we determine this coefficient by requiring that this On and Oj, with all these j, are orthogonal with each other, okay, with respect to this normalized Hilbert-Schmidt inner product. Okay, so of course this orthogonalization process depends on the choice of your inner product, and in this case we take this inner product. Okay, but anyway, so this is a new series which contains more information of the system, and intuitively speaking, On is the operator that appears for the first time in the nth recursion. Okay. Then this is the important quantity called the Lanczos coefficient, and it is defined as the square root, actually the ratio of the norms of this operator and this operator. Okay. Now this is the definition, and here comes very important observation made by Packard and others in 2019 called universal operator growth hypothesis. And they argued that, and here's a recent review, which I recommend, and they argued that the growth of the Lanczos coefficient Bn captures the essential feature of the quantum dynamics. Okay. And they say that Bn, the Lanczos coefficient, is basically constant for free models, and it grows in interacting integrable models like this, where this power delta is strictly less than 1. And they argue that in chaotic models, it grows linearly in n, basically, but with log correction in one dimension. Okay, so here is numerical simulation, and this precisely coincides with this prediction. And here's the citation number of this paper, and it's really growing rapidly, and I think it grows more. This is still October to 2025, so this will grow more. So I think you see something growing much more than linear. So something more than chaos is going on here. Okay, so what is our contribution? Well, this is our result. Okay, again, we take this very standard model of spin 1/2 in dimension 2 or higher. And again, except for the classical Ising model, we proved that there exists some initial operator A and a positive constant alpha and an infinite subset of natural numbers called G, such that this inequality is valid for any n in this set. Okay, so what does this mean? Okay, this basically corresponds, essentially means this, because if you multiply this from B1 to Bn, you of course get this thing. Okay, so this is nothing but the behavior expected in system with that exhibits quantum chaos. So we say that by this we have shown that the model shows some signature of quantum chaos represented by these Lanczos coefficients. But there are caveats, and we prove lower bound only for this product, okay, not Bn itself. And also, we do not prove this for any n. We prove this for n that belongs to this subset G, and actually this set G is extremely sparse. Okay, and here's a remark: the divergence of a this operator for pure imaginary time evolution follows from this theorem. Okay, and also our proof of this theorem for the quantum Ising model relies heavily on the idea by Tao's 2021 paper. Okay, so this is our second main result. And now here I can come back to this short story from Jiangsu. And the story goes like this. Once upon a time, there were three kings, one brief, one sudden, and one Hundun, chaos. And two kings wanted to thank Hundun, and they said, well, all men have 7 openings, 1, 1, 2, 3, 4, 5, 6, 7. Okay, but Hundun alone doesn't have any. Let's try boring him some. Every day they bored another hole, and on the 7th day, Hundun died. Okay, you can interpret this short story in whatever manner you want, but one thing I want to stress is that so far we have bored only 3, probably not very critical holes to our quantum Hundun, quantum chaos. No conserved quantities, linear Grossovian, and singularity at imaginary time. So I think it's safe. We can safely try making some more holes to our quantum Hundun. Okay, so that's our main result. And if you're interested in the proof how we make these 2 holes, please listen to the rest of this webinar. Okay, so I'm going to discuss the proof, the main idea, but I'm going into some details. Okay, so first of all, I discuss operator growth, okay, from this thing. And here's our Hamiltonian for spin 1/2 system. It's standard, but here I assume that both Jx and Jy are non-zero. This means that we are excluding quantum Ising model with this parameter. And in order to treat quantum Ising model, you need an extra idea, but that can be found in this Shanyu Tao's paper in 2021. So if you understand my proof that I'm going to explain and combine it with the idea that you can find from his paper, you have a proof for the quantum Ising model too. Okay, so let's go on. So we start from this initial operator, which is the Pauli X on the origin, so it's a single Pauli operator, and then take the commutator with Hamiltonian and double commutator, triple commutator, and so on. Delta is the Liouvillian. Oh, I'm sorry. I said Lindbladian before, but this is Liouvillian. Okay. And anyway, so we get this Bayer series, and then we do Gram-Schmidt orthogonalization to get this. Okay. Now, what you do is to take the nth recursion in this Bayer series and expand it into the sum linear combination of products of Pauli operators. So B denotes anything that is just a simple product of Pauli operators, or simple tensor product. Okay, and of course you can always expand in this way. CB are complex coefficients. Okay, and suppose that there is a product B that does not appear in delta J, J's recursion with J being 0 to n-1, but that appears in this thing. And then, of course, you can write ON in this way, and you have this, and the rest does not contain this B. Okay, then from this, you find that, first of all, this is the obvious definition. I define normalized Hilbert-Schmidt norm like this. And if you observe that these AB products of Pauli operators satisfy this orthonormality with respect to this inner product, you find that this norm is lower bounded by this coefficient because all the guys are orthogonal. So we have this inequality. Okay, and now if you recall the definition of the Lanczos coefficient, you find that this norm is nothing but the product of Lanczos coefficients like this. Okay, so our goal is to lower bound this product. So this means that it is sufficient if we can find CB, which is large. Okay, so we shall look for B, such B, which is found only in the nth recursion, which satisfies this, and also have large CB. Okay, So let's look at the simple example. So this is, suppose that this is a two-dimensional plane, and this is the origin. So I have Pauli X here, okay? And now I would like to take commutators with Hamiltonian, or a piece of Hamiltonian. First thing I do is to take this part, y0. Okay, let's call this x0. So this is x0. Okay, so I take, and y0, y1 is contained in the Hamiltonian, so I take this commutator, and of course it gives you this. Okay, so I forget about this constant here, and then what you get is zy. Okay, so this is the origin. This is the origin, and new site is added here. Okay, now you have y. So this red box means that I take commutator with yy. And the next thing you want to do is to look at this y and take the commutator with xx to get this zzx. And now you understand what you want to do. Now with this, you take this commutator with yy, and then you take this. And so if you repeat this sufficiently many times, you end up with this zzx thing. So this is the origin. You were here and you have grown. And so this is one product, okay? And definitely this appears for the first time in the nth recursion. Why not? Because in each recursion, whenever you take commutator with Hamiltonian, you can add at most one operator, okay? One Pauli operator. So this is, of course, you can get this only after nth step. Okay. So this is nice, but you observe that this can be constructed in a unique manner. So in this case, CB is very easy to compute, and you get this exactly. It's nice, but this is not very large. Okay, so what shall we do? Well, here is a better strategy. Okay, so again we start from this, and you do this game, but don't do that until the end. You stop this growing process when you grow n half of them. Okay, if this length is n/2, then what you want to do is to take, for example, here take commutator with yy. Here you take commutator with xx, and so on to get this thing. Okay, but in this case, you can take all these n/2 commutation relations in any arbitrary order. Okay, you can first take here, do it here, and so on. So this means that this b can be grown in at least n/2 factorial different ways. This is the actual real way, but anyway, it's not really different. So this is growing in at least in n/2 factorial ways. And again, obviously, this b appears for the first time in the nth recursion. Okay, so now we have this lower bound for CB. Not bad. This is much larger than this. So from this roughly implies that Bn is lower bounded by sort of square root of n. Okay. Of course, this you have this implication, not the other way around. But anyway, this suggests that we have something like this. So this is not a bad news because this is such a simple construction. So let's consider the general case. Okay, by T I denote a subset of Z2, so I'm in 2-dimension for simplicity, and it consists of n+1 sites, and it must contain the origin. Origin is here. Okay, and I denote by T tilde the bonds contained in this. Okay, so this is a set of any nearest neighbor pairs. Okay, and then this T and T tilde makes a graph in a mathematical sense, and I assume that this is connected and contains no loops. Okay, so it's a rooted tree in the graph theoretic language. And then what we want to do is we again start from Pauli X at the origin and grow a product B supported on this tree T. Okay, and then what you do is again you take these commutators with xx or yy on these bonds, and then you get this thing. And the point is that you can make this in several different ways again. So first of all, you may take this commutator or this commutator. And for example, after taking this commutator, you may take this one or this one, and so on. So what you find from this is this lower bound. So the coefficient is lower bounded by some trivial constant that you may compute, but I don't want to. So this is OK. And this nt is important. This is the number of ways that you can construct this thing starting from here. So the number of possible ways of taking commutator. OK. So in a more abstract language, this is the number of ways to grow a rooted tree. T tilt, starting from the root and adding edges one by one. And of course, so you adding bonds, adding edges means that you are taking commutators. And of course, as is clear from this construction, you always have to be your tree always has to be connected. Okay, so you add edges one by one, keeping the whole thing connected. Okay, and grow this thing. Right, so now we are interested in this quantity nt. So let's look at this more carefully. So here are some examples. So first of all, this is the example we have seen. So this is our tree, of course, and this is our root. And in this case, if you want to grow this, then the only thing you can do to be connected is just add bonds, edges one by one like this. So the number of ways to construct this thing is just one. Now the same thing, the same picture, but now the origin, root is here. In this case, you can construct this in more ways, because first of all, when you add the first edge, you can add this one or this one. Okay, so if you sit down and compute, you get this binomial number. So you can construct this in many ways. And we have already seen this. This one can be constructed in this ways. Okay, so the question is, how large can you make this? Of course, in one dimension, I think this is the best thing you can do, the largest possible thing. So we want to be, So we want to be in higher dimension. And then here's the conjecture. So there is a constant c that depends on d, but anyway, I think it's enough to consider two dimension. There is a positive constant c such that for any n, there exists at least one rooted tree it can be constructed at least in this ways. So basically, this is not very relevant. So this n factorial is important. Okay. And we expect this to be true in the d-dimensional hypercubic lattice. And I thought about this. And first of all, this is a very easy observation. If you are on the beta lattice instead of the hypercubic lattice, then this conjecture is a theorem. It's just an exercise. Okay, it's super easy to prove this. And so let me just sketch this. But anyway, the only message is that this is just an exercise problem. And what you do is first you count the total numbers of ways to grow any trees with n edges, okay, starting from the origin. So you start from here, so you can first of all add one of these three edges. So you have three. After adding one edge, then you have four. You see this? There are four edges you can add next time, four. And next thing is 5 and dot. So these are the number of ways of growing any trees. Okay, but of course you're generating the same tree many times. You're overcounting. So how much are you overcounting? To see this, and it is enough to look at the number of distinct rooted trees on this beta lattice, and it's easy to see that it's upper bounded by 3 to the 2n. How do you do this? Well, one easy way of doing this is to consider a random walk that starts from the origin and goes to n steps. And then this is the number of possible random walks. Okay, and among all these random walks, there is one that sort of traces this tree like this. Probably understand. That's why I have 2n. But anyway, this is easy. So this is the number of distinct thing, and we are definitely overcounting, and this is the estimate. Okay. So this proves that there is at least one tree that can be constructed at least in this ways. Okay. So we have n factorial. And the problem was to prove this for the d-dimensional hypercubic lattice, and I thought about this, and it was very difficult. I didn't get any result, but then I found that back in 2015, Gabe Bouch already solved the problem actually partially. So what he proved is that there are positive constants C and an infinite set G, G is for Gabe, and such that for any n in this set G, there exists a rooted tree in 2 dimensions with number of sites n plus 1, and that can be constructed in too many ways, like this. Okay, and about Gabe's construction, it's very clever, very clever. It's a total false hierarchical construction. Okay, and you start from like this column-like thing, and then you put them together to make a larger column, and put them together to make a larger column, and then you put these columns together to make much larger column, and do something like that. Okay, and anyway, by this way he constructs. This is a constructive proof. Okay, and by using this construction, brute force construction, he proved this, but not for any g, any n. Okay, so this n must be in this set G, and actually this G is infinite, but it is rather sparse. Okay, but anyway, what do we learn from this? Well, let's go back to the previous slide. So this is a slide where we discuss general strategy. So first of all, recall that this, okay, this is the object we wanted to lower bound, right? This is a product of the Lanczos coefficients, and it's equal to this normalized Hilbert-Schmidt norm of ON, and it's lower bounded by this coefficient of a product B. Okay, and then for a given B, this is corresponding tree, and this CB is lower bounded like this. So some constant times NT. Okay, and now Bauch gives the lower bound for this NT. So combining this, and Bauch's bound, what we found is this. If n belongs to this set, then this lower bound is proved. Okay, and this is proved for a large class of models in dimensions 2 or larger. Okay, so that's the basic idea of the main part of the proof for the operator growth. Okay, let's consider imaginary time evolution. Okay, now right, so I consider this general Hamiltonian, and I take initial operator, which is local and self-adjoint and normalized. Okay, but actually we finally set A to be x at the Pauli x at the origin. Okay, and H lambda is the restriction of Hamiltonian onto a finite region lambda. So as I said before, this is just a finite dimensional matrix, and this is 2. Okay, so this is imaginary time evolution, and again, by using only the linear algebra, you can expand this into the nested commutator. But this is a standard formula, but if you're not familiar with this, I recommend you to just Taylor expand, consider the low, some terms in low Taylor expansion of this thing in beta, of course, and then compare it with this right-hand side, and you're convinced. Oh, of course, you can prove this. This is an elementary rigorous formula. Okay, this is Liouvillian. Okay, and we are going to prove that the operator norm, not the normalized Hilbert-Schmidt norm, the standard operator norm of this thing diverges as lambda goes to infinite. Lambda tends to infinite hypercubic lattice, provided that the absolute value of beta is large. Okay, and here's a series, and our delta is defined so that this is always self-adjoint. But anyway, this here has, sort of oscillating sign or phase factor. So this lower bounding, this is non-trivial task. And that's why Bauch invented his own model in which he does not suffer too much from this sign problem. Of course, it's highly non-trivial, but still, the model was easier to treat. Okay, but there is a better way that I learned. I was inspired from all these papers about operator growth. Okay, so this is something we already discussed. And then what I do is to take the inner normalized Hilbert-Schmidt inner product of this thing and the initial operator. And of course, since this is convergent, we have this convergent series. Okay, now I note that this Liouvillian with respect to this normalized Hilbert-Schmidt norm, inner product is anti-Hermitian. If you bring it here, you get minus sign. So by using this repeatedly, first of all, when m is even, you can rewrite this in this form. Very nice. Okay. And when m is odd, you find that this is 0. Okay. This follows easily from this fact. Okay. When C is self-adjoint, this is vanishing. You get this immediately from this. Oh, by the way, this is, of course, very super easy. You just plug in the definition and you find. Okay. So now we can rewrite, but by using this, we can rewrite this series in this form. So I wrote m as 2n because we know that m, we only need to consider even m. So this is the exact series. And as you see here, we have norm squared. So this is good news. And we have sum of non-negative quantities if beta is real. Okay. So now we want to lower bound this. So first of all, for any finite lambda, finite subset lambda, we take n such that nth recursion of this finite volume Liouvillian is equal to the nth recursion of the infinite volume recursion of infinite volume Liouvillian. And of course, there is such n because if lambda is sufficiently large, you don't see that you are in finite box when you take commutators. Take many commutators. But if you take too many commutators, then you go out of this finite region and you find that your Liouvillian was for finite lambda. Okay, and so for this reason, as lambda goes to infinite lattice, n tends to infinity. Okay, so this is an important observation. Now, okay, so this is the formula we knew. So from the first of all, okay, from this fact, you can replace this, or you can lower bound this quantity by replacing this by n and changing this delta n to simply recursion of Liouvillian for the infinite system. Okay, so this is a standard notation. Let me define the moment mu to n like this. Okay, so this is Liouvillian without lambda. Okay, and then this is, as I said, lower bounded like this. Okay, now we always use Schwartz. If you use the Schwartz inequality for this, you get this. And by assumption, this normalized Hilbert-Schmidt norm of the initial operator is 1. So this is upper bounded by normalized Hilbert-Schmidt norm. And it's easy to find that this norm is upper bounded by the standard operator norm. Okay, so we get this. Okay, so this is something we wanted to lower bound. This is the operator norm of imaginary time evolution of the initial operator A. Okay, and this is lower bounded by this. So now we need to know something about this. This is moments. But here is the good news. Moments are related to the Lanczos coefficients in this way. Okay, and actually you don't have to understand this. But if you know what dict path is, this is an interesting expansion. Okay, so mu to n is expanded in terms of Lanczos coefficient in this way, and dict path is something like this. So you always go to the right by one step, and you can either go up or down like this. But you can never go downstairs. Okay, you can only be on the ground. So you can do whatever and come back like this. Okay, but anyway, you don't have to understand this. Anyway, we have this exact expression for mu2, mu4, and for most importantly, we have this. This comes from dict path, which goes like this and goes like this. Okay, so we know that this mu2n is lower bounded by this product of Lanczos coefficients. Okay, so this is our target. It's lower bounded like this. By using this, it's lower bounded like this. And now we choose our initial operator to be Pauli X at the origin and consider the model that we are considering and restrict this summation to the intersection of this interval and Bauch's set of of positive integers. Okay, of course this is an infinite set. Okay, so then you can use this lower bound that we have proved. So we have this. So you reorganize this to get this. Okay, you have some and this. Okay, but this is nothing difficult. This is basically 2 to the minus 2n, I think. So you can combine this with this to find that since G is an infinite set, this sum diverges if this condition is met. Okay, so this proof of the divergence of this as n goes to infinity, which means that lambda goes to infinity, works whenever we have this lower bound. And this lower bound has been proved for xy and xyz model in the previous part, and it can be proved for the quantum Ising model by using Chan-Yu-Tao's result. Okay, so we are done. And I can safely go to the summary slide. Well, this is a short summary. So we treated this standard spin 1/2 model in d dimension, but in dimension 2 or higher. And except for the classical Ising model, we proved that the imaginary time evolution of a local operator exhibits a singularity at a finite imaginary time. And also the Lanczos coefficients Bn are lower bounded like this for any n, okay, in this Bauch set. Okay. And so we can say that quantum spin models in dimension 2 or higher generally exhibit chaotic behavior. And we can partially prove it like this. There are many, many remaining issues, but one thing is to prove the existence of trees that can be grown in too many ways for any number n of bonds. Okay, so our proof still relies on this very clever construction by Bauch, but we want to have, well, this doesn't solve any big problem, but it makes me much happier to do this for any n. So this tree problem and the lower bound of nt problem is still very much open. Okay, and I hope that somebody clever can come up with a non-constructive proof. Okay, and also it is interesting to develop a new technique to prove a lower bound for the Lanczos coefficient Bn itself rather than the product. Okay, I think we need some new idea, and that will be very interesting. And also, this is not related to this this webinar directly, but it's very nice to extend Naoto Shiraishi's method to exclude the possibility of not only local conserved quantities, but also quasi-local conserved quantities, which have sort of exponentially decaying tail. And of course, this is a very big problem. We want to prove some dynamical properties which are directly related to quantum chaotic behavior. Okay, let me finish this webinar by showing this slide from Jianzu again, and let me invite you to add some more holes, at least 3 more holes to our quantum chaos. Okay, so that's all what I wanted to say. Thank you very much for watching. Goodbye.